Welcome to the Masterclass on Heightfields. In Houdini 16, we've added a new capability for our volume primitives, which we call Heightfields, which allows you to take a two-dimensional volume and reinterpret it as a height field. So let's first look at what these look like. So if I start off with a normal grid, in this case I have a 500 by 500 grid. And you can see if we zoom in that there's a lot of points and edges on this, and apply some noise to make a sort of rough terrain looking object. The problem is we have, for this 250,000 points, 1 million vertices, and so we're using 20 megabytes of memory to specify this grid. And this is a lot of wasted space because most of these are just simple quads, and so a very simple vertex arrangement. If I change that grid into a polygon soup, we can drastically reduce the memory consumption because it doesn't have to store the vertices twice, or 4 times in this case. And so we're down to 250,000 points, same number of vertices, and only one primitive in one poly soup to represent the whole thing. This also makes it easier to work with because I can treat it as one cohesive unit rather than worrying about the internal topology. But if I look at the resultant geometry spreadsheet, we notice there's a lot of pointless data here. The z values are almost the same everywhere, and the x values keep cycling through the -5 to 5 values as they go over from one side to the other. So we really didn't need to store all of that data. So while this has been reduced down to 12 megabytes from the 20 megabytes before, it could still get a lot lighter. To do this, we can create a volume primitive. And so here I have a simple volume primitive, which is 500 by 500 in size. You can see 500 by 500. And again, we have only one point and one vertex and one volume with 250,000 voxels. Now, if we treat this as a normal fog volume, these would have sort of 0 to 1 values. There's no reason why we can't store other information in this. And we often do that in things like the pyro solver, where we'd store temperature or burn type values or even velocity values in here. So we can also store our height values. But how can I see in an interesting fashion what is happening with these height values? So we've added to the properties page a display mode. In addition to displaying it as smoke or isosurfaces, you can also choose to display it as a height field. And this doesn't do anything particularly interesting when it's all 0. But if I apply the same noise function, we can see in the viewport what looks like the same displaced grid as we had before, except this time there's no actual polygons being used for this. So again, to switch back to the polygon base, we can see the individual edge lines. And to go back to the height field, we just have a single primitive being displayed. Of course, in practice, when it goes to the video card, it is generating polygons just in time. We're able to use things like the GL tessellation shader to produce these on the video card itself, greatly reducing the amount of data needed to transfer. So when we look at the resulting object, our memory usage is now down to 1 megabyte, which is 12 times smaller than we had before, or with polysoups, or 20 times smaller than we had with polygons. So now let's increase the resolution of this. Because we had 500 by 500, let's just bump it up to a 2000 grid. And now we are up to 15 megabytes in usage. Now, an important thing to note is because we are using our volume primitives, all of the tools of our volume primitives are still work. And so I can do something like a volume blur. And this has got way too big of a radius, but let's cut it down. And we can see we can quickly blur out our entire volume. The edge conditions are being used there, so I can tell them to use, for example, repeat or streak edge conditions. Or I can do things like volume resample. And here I can change the effective resolution. So currently it's 2000, but I can cut it to maybe a quarter of the dimension. So it's changed the resolution scale to 1/4. And we can see here we've done a box filter of the entire height field because all of the volume tools still worked. Another thing we have with our volumes is all of our volumes are tile-based. So we break them into 16 by 16 by 16 tiles. This being a two-dimensional volume, this means it's 16 by 16 squares. So in particular, this allows us to compress stuff that's constant value. So while we had 15 megabytes for the 2K volume, when it was empty, it was only 400 kilobytes. And this is an important point because you might have extra volumes storing metadata, like whether or not something is masked. And it's important to realize that doesn't cost as much as the full height resolution does. The other thing we can do is use the volume compression settings, which let us do things like quantize our volume based on their local values. So I can do things like update the compression settings and switch to 16-bit floats. And here I don't really notice any difference, but I'm using half the memory that I did before. It's going to be a bit slower to process because we have to unpack from 16-bit float to 32-bit and back again every time we access a voxel, but it does save you half memory right out of the gate. We can also use quantization, which is where if the points within a tile are within a certain distance, we basically just reduce the bit depth of that tile. So it's something like 0.02. As we increase this, you can start seeing it getting errors. Now this is getting very noisy right now because the quantization was designed for smoke volumes. And in smoke volumes, you can do dithering, where you can hide the fact that you've got a harsh 0-1 value by alternating every other voxel. Now this doesn't work very well with Heightfields because it shows up as this really high frequency jumbling. So instead we can turn off the dithering and we can see instead staircasing occurring, where the voxels are being forced into one value or the other. So in this particular case, we've reduced it down to 1.5 megabytes because we've reduced the number of bits stored per voxel quite considerably. With something like 002, we have something which has very few visual artifacts, even these valleys. We're still seeing good results, and we're down to 4 megabytes of usage. So this is, again, that's down from the 1/4 the amount of memory we used before, or probably about 1 byte. I guess that's on average 1 byte per voxel, which is equivalent of storing sort of an 8-bit image. Now, when you work with the grid and you needed to get extra data, we again have this grid here, you want to store something like a rainfall attribute of how much rain will fall on any particular location, which you might want to paint in, or you might use a attribute VOP with a static noise to generate. You do this by creating another attribute. We can see this in the geometry spreadsheet show up as the rainfall attribute here, which varies over all the voxels. And we can then visualize this. This is a visualize node. And by setting the visualizer to rainfall and ramped attribute, I can then see in the viewport what the rainfall attribute looks like. The same is possible in the new Heightfield world. Instead, however, because if we look at the thing here, there's no room for a point attribute for rainfall because there's only can be one value for the rainfall point attribute for this entire grid. We need something where we can specify rainfall on every single voxel. We can do that by creating another volume. I've wired this into the parent volume to allow me to inherit its size. I do have to specify its sampling divisions to also be 500. And now I can set its values. If I look at this, I'm now looking at it as a fog volume, so I can see the rainfall as a 0 to 1 gradient. And if I merge them together, now I've got a single piece of geometry which has 2 volumes in it. One storing my height and one storing my rainfall. And if I look at my volume 2 up here, we can see I've set the name to height. And in volume 3 here, it's been set to rainfall. And when I look at the merged result, I can see I've got 2 named volumes here, one named height and one named rainfall. And this is stored in the name primitive attribute. By naming them this way, I can now merge them together logically and have them displayed in the viewport as a single entry. This is what the pyro simulations, for example, would do when they'd have, for example, a temperature field and a density field, and you want to display them both at the same time, but have the temperature cause the density to change color as it got hotter. So I can use the same volume visualization node. And here I want to tell it to switch to height field or set it to no change. But my density field is going to be height, though that's kind of misnamed here because it's my height field. And my diffuse field to control the color will be the rainfall. And now it's doing a 0 black to white ramp. So I can use one of the presets like infrared. And now I've got this displayed. And if I change the rainfall result, this will change automatically, regardless of where I am in the network. Because this is kind of important for working with different layers, we made a new node called Heightfield visualization to make it easier to set this up. So with the Heightfield visualize, I can tell it to update the tinting to be a custom tinting, and just turn off the material use. And the default is to use height and mask, but I can change this to use rainfall. Now I've got a white to red mask. So again, switch that to infrared based on rainfall. But we also have an option to do a more complicated visualization. This is with the material choices. And so if I display the material, we can see it generate a color based upon the elevation. And the compute range will quickly let us set it up to the range of the incoming simulation. So here I can have it brown to gray. And I can change where the cutoff points are. I can also add new layers in. So if I want rainfall done with cyan, I throw that in, and now we can see an overlay of cyan on top wherever there's rainfall. This is also, you'll notice, is less specular because the shader we're using has very little specularity on it in order to make it look more like ground plane would look like. We're going to go through with this tinting one anyways for the additional stuff. Now, if we want to manipulate this rainfall attribute, which is really a separate volume, we can use a wrangle if we like wrangles. So I can do a Heightfield wrangle. And this is really a volume wrangle, which has been relabeled to make it easier to type in. And I should point out, when I did the tab menu there, I just type in HF, and this gets me all the Heightfield nodes, which is a bit faster than typing in Heightfield or searching it out. And then wrangle would be WR. In the Heightfield wrangle, I can use the automatic binding to refer to the named fields. So I can do rainfall equals 1 minus rainfall. And this will get the complement of the rainfall, so invert the sense of it. And so now wherever it was dark is now light, and wherever it's light is now dark. If you prefer VOPs, you can do the Heightfield VOP. And this again is a renamed volume VOP because we're just working with volumes here. And inside this, I can dive in, and we can see there's already a binding here to read in the height, because we were often not outputting density anymore, we're outputting other attributes. So I can put in here a bind to bind the rainfall parameter, and then do a complement to do the 1 minus operation, and then to write it out again, I do a bind export, and I set this to rainfall. And the result is the same complement operation. Now, as mentioned, there's quite a few different nodes that can be applied here. There's quite a few that are designed working around what we call layers, which are these separate named 2D volumes. So Heightfield copy layer, for example, lets me easily copy one layer to the other. So in this case, I can copy this rainfall layer into a mask named layer. So after doing this, we can see we have 3 volumes present: the height, the rainfall, and then the one we just copied for the mask. And now I can do a Heightfield visualize again, and this time I'm going to reset the tint into the default. By default, the height fields are set up to no change, are set up to have a red to white tinting of the mask field. So I had earlier set this up to display the rainfall field, so I'm just setting back to the default idea of displaying what the mask field is. So similarly, I can do a Heightfield remap. And here, when I want to remap, I can specify a layer, and this will let me select the mask layer. And basically, if I want to complement it here, I can just set the output range to be the opposite of the input range. And displaying this will show me the, again, inverted, back to where it was to begin with, mask field. Now, there's plenty of other remapped ones. As I said, volume blur is present as a option, but we have Heightfield blur, which we're applying to the height field, and specifically the height layer is what is blurred. Similarly, I could instead blur the mask layer, and if I turn this up, we can see the pink spread out and become less distinct. Or I could blur the rainfall layer, which will not be immediately visualized because I'm not showing that layer right now. It's blurred behind the scenes. So back to the height layer to blur. And we might want to restrict it to only blur in a certain area. So I can use this second input as the mask input. And now it'll blur wherever the mask is present. So you can see the blurring occurring only with the positive red mask area. Now there's a paint button here, and this will actually put down a Heightfield paint node, which lets you then paint out certain areas you wish to apply additional blurring to. So this chain of operations here, like copying layers, visualizing, blurring, applying garbage mats, is sort of like a compositing workflow. And we already have a compositor in Houdini, and so it's natural to want to use some of its tools to further augment your work with Heightfields, either to pre-process images you get that are Heightfields, or to generate images, or just to use some of the cool compositing tools we have. So in this version we have, I can put down a compositing network, so a COP2 network. And if I dive into this COP2 network and switch the viewer here set to scene viewer, I have to change it to the composite viewer and put down a node so I've got something to look at. We can see we've got a file node here loading up the default butterfly, and we're able to switch our current plane here, and we can see what the image is inside the network editor. Now this is inside this COP2 network. And so one of the new COPs we have is a SOP import COP. And this allows you to grab information from a SOP network and bring it into the compositing world. So I can select here my parent output, which would be that Heightfield blur. And we can see already it's brought it in to our native COP space. So our default resolution is HD 1920 by 1080, and it's bringing it in as a color channel. So you can see I've got color and alpha brought in. But in my source world, we notice I have a 500 by 500 grid, and I also have 3 separate channels: height, rainfall, and mask. So let us dive in and see what how to get those in. There's an option here to set the resolution from the SOP. And so an image here, it hasn't overridden the size. But if I do that, it will override the size and set it to what the SOP resolution is. So I have the native 500 by 500. And it's also set the planes from the SOP. So the default planes are to use color in alpha, which is what people expect when they're compositing. But if I do this, I've then actually got some very specific planes. I've got height, rainfall, and mask 32. And so here I can switch between rainfall and mask and see the different values. I can also, in the network editor, actually switch between them very easily and see what the different results are. Now that I'm in COPs, I can use some of the cool COP tools. In particular, there's a nice radial blur. And if I apply the radial blur, we can see we've twisted the image around and made a nice blur effect. And when we look at this COP network as a whole, there's the display flag, which is what's used for showing to the viewer. And it's possible using the shift mouse button to have more than one display flag, which you often do to compare two COP networks together. And a very useful thing when you're comparing them together is the option to link scroll in 12 views. Doing this lets you make sure you're looking at the same part no matter where you are. So that's this button over here. But when we want to export this to somewhere else, it's important to know which node you're going to export from. And that's the orange output node. And so currently it's the file. I'll move that over to the radial blur. So that's the one we're going to export. And if I go up a level back to the SOPs world and switch back to our 3D viewer, note that the COP network here is, in Houdini 15 we had a COP network here, but there would have been no flags on it. It was a foreign management network. But now it is actually a SOP, and so you can actually display a COP network. And what does it mean to display a COP network is you get a grid back, and you can see this grid has lots of polygons in it because we've set it to mesh mode. And if I go to the details view, we can see it has attributes for the height, mask, and rainfall. So all the attributes of the COP network were brought over, and it has the 250,000 points you'd expect. Instead of a mesh, I can bring it as a volume slice. And this gives me a 2D volume, which lets me then have this as a nice simple 2D volume, again with height, rainfall, and mask. And there's also an interesting option here called volume. And volume max will create a 3D volume, but the third dimension will be the time dimension. So any particular COP network might be a sequence of frames, like say 50 frames long, and then you'll have something that's 50 deep in the z-axis, and each layer will be another frame of time. So in this case, of course, we want only a single layer, so this is correct. Now we need to change this to view as a height field, so I can use the primitive SOP, and this has the option on it to on volumes to adjust the visualization, and so I can switch that to height field. And now I'm seeing it as a height field, and we see it's a huge, massive thing. I'm actually seeing all three of them as height fields, so the height, the rainfall, and the mask. So let's switch that to only do the height. And this looks very high compared to what we had before. That's because previously this was spread over a very large area. So you compress this large, what is it, 10 size 10 square down to size 1, and it's going to look very tall. But we just need to change the size here back up to a scale of 10, and now we'll have much closer to what we expect the result to look like. Now there's another way of bringing in height field geometry, which is usually more straightforward, and that is the height field file. So this can be used to load files from disk, but it can also be used to source files from COPs. So in particular, I can again point at my COPNet here and set my size properly to be 10. And now I've brought in my file as a brand new height field. I can also layer it on top of an existing height field. So this is particularly useful if you want to bring in a little patch of soil into another one. And so here I've layered it on top, but I want to, and it's layered on top as a mask name. So I can layer on top of height, and now it's going to add to the height field. And when I'm layering it, I get some controls for where I apply this displacement. And so I can set it as a rotating around a bit. But the layer mode can be set to replace, in which case I have only the new one. And you can also set what the border type is. For example, I can repeat the border. And then if this was a tiled texture, it would nicely tile forever. It's not tiled nicely, so we get seams obviously on the edges. In addition to working at the SOP level with 2D volumes, we've added a new option at the object level. There's now in addition to a COP network, a COP plane network. COP plane network produces a object at this level, but it's an object that is a COP network, and so you can use it as sort of a background stencil. So I can increase my uniform scale here to make it somewhat larger, and this butterfly I'm seeing here, if I dive in the COP2 plane, is a result of this network chain in here. So I can do something like a bright, make this the output node, and then brighten up what my stenciled image is. I'll do a blur. You can see the result is placed at the higher level. You can also switch to wireframe and it stays displayed. So this is quite fun if you need to have reference material you bring in to your scene, and you can position it in space freely, unlike stuff that's tied to a camera, and place or layer it wherever you wish and drive it from a COP network. Now, as I mentioned, you can move files from disk as well. So where can you get some interesting files for this? Height field files can be found online in many different formats, and often it's a little bit of work to figure out how to get them converted in properly. One good source is opentopography.org, and they've got a whole bunch of different height field sections together. Each one, they have the appropriate citations you need to do to use it, because it's different depending on where the data came from. In particular, raster data is particularly interesting with height fields, because that's what height fields are basically images. And so if we go to global data, there's, for example, the shuttle radar data. And this rather impressive system lets you just zoom in somewhere. And so if I go to my favorite volcano, which is Mount Aso, somewhere around here, you can select your region of interest. and generate the resultant data. In this case, it would be 125 kilometers squared, and the output format is GeoTIFF. GeoTIFF is a TIFF. The nice thing with the TIFF file format is it stands for tagged image file format, and this allows you to add arbitrary extra metadata to the tagged area, but programs that don't understand that metadata can safely ignore it. In the case of GeoTIFF, they add a lot of stuff for knowing exactly where in the world it is and what the height information is stored as. And Houdini doesn't support reading all that metadata, but you can get the raw image in and rebuild some of that metadata yourself. So you'd submit this, and then you get back a zip file which has a TIFF inside of it. So I've already done that previously, so I can just here do a Heightfield file and select a file from disk. So I have this output srtm.tiff, and we default to a 1,000 size grid, so this is going to look very flat and boring because we've got the wrong height and wrong size. In this case, I don't know its exact dimensions, but I can go to grid spacing, and this way it'll use the resolution of the file on disk and make each pixel this big. And so in this case, I know it's a 30-meter source, so setting this to 30 will immediately give me the rough approximate size. Still perfectly flat though, because what Houdini doesn't know is what the vertical scaling is. This is something that can differ depending on your different file sources, and just because this is GeoTIFF doesn't mean everyone encoded it the same way. These particular ones though tend to be encoded as 16-bit with 1 meter per value in the white point, so then the height scale becomes 65536. And now I have the mountain range pop out into existence. It's always good to just double check you've got the right rough area here. If I middle click, I can see what's my maximum value, 1579, so 1,580 meters or so. And then I can compare that to something like height of Mount Osso. And the internet tells me it's 1,592 meters. That sounds like we have successfully got it close enough for our purposes here. I wouldn't use this to fly a plane, but it's definitely good for my purposes. So Heightfield file, we've loaded this, and this is pretty low resolution still. It's 376 by 303. And so let's try and do some up-resing of it. So I can do a Heightfield resample and resolution scale of ×4. And now I've got something of significantly higher resolution, 1500 by 1200, but it looks pretty much the same blurriness because, of course, that's the goal of increasing the resolution smoothly. To add some more detail, I can just have it erode for a bit. So I do a Heightfield erosion. You'll immediately notice this adds a visualization to it, and so I get this strong terracing show up. So I can just go to the visualization and recompute the range. And this being, Mount Osso is actually pretty green, but I'll instead make it gray because that's what most people expect. And if I hit play, we can see a river network start to form. More importantly, this sort of carves up the detail, carves up the surface, and gives it a little bit more detail and finer results on the results, so it looks more interesting. Now we have this. How can we get this out of Houdini into other places? The first place you might want to send it is Mantra, so you can get images which you can use elsewhere. So if I switch to the IPR and go to the IPR viewer and just select a section for rendering, we will notice it will render the same way as it looks in the viewport. This is because we're using a material which is Mantra compatible for the GL viewing. It's the same one we're using for Mantra, and so we get a nice one-to-one correspondence there. And of course, you can build your own materials through /mat, which can use these attributes in any other strange ways. But for this purpose, we got the water and debris colored, and we can see the result in Mantra without having to do any additional work. If you need to go to other packages, though, that don't understand our volumes, you might need to convert back to polygons. So a Heightfield convert, or convert Heightfield, handles this. By default, it will convert it into polygons. And of course, you'll use a lot more memory this way, but it does mean it's fully compatible to everything. Of particular note, our original had a whole bunch of height fields, a whole bunch of layers, height to mask, bedrock, down to debris. And when we convert that to polygons, we turn each of those layers into an attribute. So all of that data is still there on a per point basis in this new world. We also add a UV attribute, which is useful for your shading, which is just basically a 0 to 1 UV mapping the whole area that was generated. Now, one problem, of course, is I saw beautiful colors here, but I don't see any beautiful colors here. It's all turned gray. What we have is big point colors, and that will basically just apply the same sort of shader and give you roughly the same result. Though usually you'd want to just read those native attributes to do your own thing. An option on this is to extrude the base. Because this is just a rough surface representation, sometimes you need an actual 3D solid out of your terrain. And so this extrudes out a bottom. And so you end up with something with a flat bottom, which you can use if you need to do collisions, or maybe you want 3D print this. Now you've got something that you can actually slice and print. And again, because we converted to polygons, we're using a lot more data. This was 53 megabytes before, and it ballooned up to 1 gigabyte after generating the base and all the side information, all the color data. Now there's also an option on the convert height field. So sorry, I just miswired that. So on the convert height field, in addition to generating polygons, we can also generate VDBs. And VDBs are a volume representation which is designed to store sparse data. Now, the case of our 2D volumes are not actually that sparse because they're dense in the two-dimensional sense, even though they're only a thin surface. But if we think of this as a purely three-dimensional surface, that surface layer actually becomes very non-dense, and that's where the VDBs become quite useful. So this converts us into a VDB surface, and again, we lose our color information because there is no per point color place to place it. There's a single VDB generated, which is the surface of this field at the same resolution our original one was. And we know that it did increase in size compared to before because we have to store the actual three-dimensional location of all the voxels, even though we only do it in a very lightweight manner. But you know, we have all of the detail we had before has made it across in this process. The big advantage of VDBs is we're able to do things like work with actual real three-dimensional topography. So with height fields, you can't have any overhanging points, but in VDBs, you can. So for example, if I take a rubber toy and make it significantly bigger, a giant rubber toy, move them up somewhere. And I want to merge this in with my base terrain. I can convert them to VDB from polygons. And here I can use the second input to point to the convert height field. I want to do this first because the default voxel size of 0.1 with something this big will take me a long time even to interrupt to quit it. But by providing a reference VDB, I make sure I use this guy's size, which happens to be 7.5. And then if I change my resolution of this terrain, I'll naturally get a higher, lower resolution of the rubber toy. So doing this, I've got the rubber toy converted into VDB as well. And to merge the two together, I can do a VDB combine and set it to the SDF union. And now I've got a single surface which has this sort of three-dimensional overhang built into it, and lets me do a lot more interesting operations with it. Now let's go back to the height field here. Now I can do other interesting things with this. In particular, let me go back to frame 1 from my original geometry. I can tell it to be a collision object in DOPS. So there's a terrain object option, which has been there before, but now is aware of height fields. So if I select the terrain object and select the grid and ask it to be turned into a collider, I'm going to get a new dot network. And in this dot network, it will use this terrain object. It has a use Heightfield flag being set, and so it's going to then not create a SDF collision of the full dense result. It's going to create a SDF collision that only has the Heightfield. So if I go to the SDF representation, which is what DOPS uses internally to build these volume representations, there's an option here to represent it as a Heightfield, which means it only stores the 2D volume, and whenever it needs to know a distance, it looks it up on the 2D volume rather than having to actually build an explicit 3D representation. The important point is that this is very fast and lightweight compared to trying to do it with polygons or with a dense SDF. As you can see, it generated it quite quickly right there. I can now, let's add some spheres. So I'm going to just put a new polygon geometry in here. I'm going to have to make this pretty big because our scale is very huge here. So 100 size spheres. Make a equally huge grid. Maybe 1,000. And copy those spheres to the points. And let's make sure they're not colliding to begin with. There we go. So we've got a whole bunch of ball bearings, and we're going to now drop this onto the terrain we have. And we can do that with rigid bodies, turn into rigid body objects. Select our spheres. And then if we hit play, it's going to move very slowly because it takes a long time for things to fall from such a high height. It's the trouble of working on such a large scale. But instead, I'll just push up gravity. In other words, make the centimeter scale rather than meter scale, so everything gets smaller. So 100 times more gravity. Now when I hit play, they will fall quickly and roll off. So this is the Bullet simulator. Bullet has a built-in support for height fields, and so it can just natively collide and roll along these height fields very efficiently. The same happens for Flip and for our Pyro and our other simulators. So we're quite happy with our newfound support for height fields inside of Houdini. There really are a new type, can be thought of as a new type of primitive, a new way of working with two-dimensional data. Two-dimensional data can be worked with in compositing in the COPS system as before, but it's also something that you can start thinking about doing inside of SOPs as well. I think there's a great potential for these to be used in very strange and wonderful fashions that we haven't thought of. So I'm really looking forward to how you end up using it outside of just terrain. I mean, that's why these nodes are called Heightfield nodes and not called terrain nodes, because there's really the potential for using this in a quite an amazing way. So thank you very much for listening. I hope this was of interest.